we continue studying different types of regressions. Previously, we discussed regressions that are just called linear regressions, and in these linear regressions, we discussed a problem when we have some variable that we are interested in, and we have several other variables that are associated with our variable in some way, and we want to study this this association. And today we continue discussing this framework, but with different types of variables. So let me share my screen. So today we will discuss logistic regression. And let me put it in the general framework. First of all, what problem do we discuss? Previously, we discussed linear regressions. Where we studied relations like y equals to beta naught plus beta 1 x1 plus and so on plus beta n xn. And in this case, we assume that we have several variables like x1, x2, and so on, xn, and variable y. And we have some values here, and we have value here, and so on. And we want to predict this value of y using these values. So we believe that there is some kind of functional relationship that y depends on these values in some way, and we want to uncover this dependency from our data. So we want to find what is the rule that allows us to find y using knowledge of these variables. But this framework works if everything is numeric. If this variable is numeric and these variables are numeric. On the previous lecture, we discussed how to include some categorical variables, independent categorical variables, into our model. We did it by encoding of this independent variables categorical using dummy encoding, and so converting each categorical variable to one or several new variables which are in a sense which are just numeric, but they just take two values, zeros and ones. And this is a rather popular approach. But this was a discussion about these variables, independent variables. So let me recall that we call these variables independent. And this variable is dependent. So previously we discussed what happens if we have some categorical independent variables. But now I want to discuss another option. What happens if y is a categorical variable? What if y is categorical. Our current problem is like the following. We have some categorical feature of some observations or some objects, and we want to be able to predict this categorical feature from other data. For example, an example that is close to linguistics, for example, we want to study, is it true that a particular person speaks a particular language? Like we study people in Russia and we are interested in, do they know English? In this case, probably our data set looks like the following, like age, um, probably education, um, maybe gender, and some probably other variables. But finally, we have a variable like English. And we believe that we have something like uh, something like this. It is possible that we have some numeric variables here, some categorical variables here, and finally we have a categorical variable as our dependent variable, the value that we want to predict. So we want to understand in our study how these variables influence this variable English, which factors can be used and in which and how can they be used to predict this English value. This is our problem. And what can you suggest? How can we plug this categorical dependent variable into our model, into linear model? Is it possible? Any ideas? Any suggestions? No, 0, yes, 1. Yeah, that's a first correct idea. First of all, we can encode these values. If we have just a binary variable, then we can encode them as just 0 and 1. If we have a categorical variable with more than 2 levels, so not binary variable, but some more complicated thing, then well, it is a little bit complex case, and let us begin with binary outcome. So assume that y is binary, like yes or no. And then we can encode for example, yes, 1, no, 0. Now, basically, we have instead of instead of categorical variable, we basically have something that can be interpreted as number at least. Well, if we have categorical variable with more than 2 levels, yes, you can encode it as 0, 1, 2, 3, and so on. But I'm not sure that you will get meaningful results. This is the same case as we discussed previously when we discussed encoding categorical independent variables, because the problem here is that numbers have some numeric meaning. They have some relation between them, and actually this formula relies on this meaning. So if you have, for example, 3 categories like 3 cities, you cannot just encode them as 0, 1, 2, because basically it means that you have assume that you have 3 cities, Moscow, St. Petersburg, and Novosibirsk. Then if you encode them as 0, 1, 2, it means that you have some scale where a particular person can be more like Novosibirian or more like Muscovite, and in the middle there is St. Petersburg. So you assume some relation between these values, which if they are just arbitrary, then probably this is not a correct way to encode it. But now if we have just 2 values, then we can encode them as 0 and 1, and this is fine, because 0 and 1 do not have any special values, any special meaning, any special relation between them. The distance between them is 1, but it is not specified what does it mean, what is the unit of measure. So if we cannot compare this one with anything else, then it doesn't matter that it is 1. It can be 2 or 3, and the result will be the same. But anyway, we encode them as 1 and 0. Then we probably can just plug this formula as is in just by considering this variable as 1s and 0s. But let me draw a picture. For example, I will use only 2 variables now, this age and this English, which is encoded in this way. Then I can get something like this. I have age, and I have some values. So this is my English. And I have some values. Something like this. So all values of English are either 0 or 1. So we have points only on these 2 straight lines. But we can draw this picture. This is a completely meaningful picture. And then we can try to find a regression line like we already discussed when we discussed linear regressions. So we can find some line. We can use ordinary least squares, so we can minimize these differences, squares of differences between this point and this line, like these differences. And basically, yes, it is possible to do it. But this model is not very interpretable. Because, okay, we have some line like y equals to beta naught plus beta 1 times x. But let us think about, for example, this point and the corresponding value of y. Our model predicts that for a person with this age, let me put some numbers just to be able to speak about numbers. And let us speak, for example, this value 10. What model, if this model is like this one, what it says about people of age 10. If we see this line, then we have to say that the model says that, well, something that is related to English knowledge for people of age 10 is negative. So it means, for example, that we cannot interpret these values that are predicted by our model as, for example, probability for a particular person of this age to know English. So what model, this linear model predicts? It is not clear. At least it is not probability. It is not probability that a particular person knows English. Why I'm so sure that these values cannot be interpreted as probability? Why it is not probability?
Probability cannot. Sorry.
Cannot
be less than 0.
Сейчас, нам нужно что-то сделать.
Yeah.
Простите, у нас проблемы технические.
Okay. Yeah, I see. I see it is YERFT 0. Yes. It cannot be less than 0 because probabilities cannot be negative, and it also cannot be larger than 1. Also, just due to our definition of probability cannot be larger than 1 because probability is just a kind of relation between. It is just a fraction that has to be less than 1. So when we use this model, it is not clear what this model predicts. So we want a bit different model with a more clear interpretation, with more clear meaning of what we predict. Because otherwise, well, basically it is possible. If you're interested only in the predictions, basically it is possible to use this just OLS model in this case. You can just, for example, say that if this value is larger than 1/2, then we will predict 1. And if it is less than 1/2, then we will predict 0. And we just will not give any interpretation of these numbers, of the numbers that we predict. We just convert them to these values, and that's all. It is possible, but we want something more meaningful. So how to make a model? This is because probability cannot be negative, for example. And actually, this problem arises in any case if we use linear model, because any linear function gives us a function that take any possible value, negative value, positive value, all positive values all over the real line. So we cannot use this linear model, at least in this way, to get some meaningful predictions. So we want to do it in a bit different way. Are there any questions so far? Mhm. Okay, so we can continue. So our goal is to, in the same setting, I want to create a model that will predict probability of getting y equals to 1. So let us assume now that we have only one independent variable, and this variable is numeric. Like I will consider the same case as here when we have just age and English. We can include other variables later, but now let us think about this model. And I assume that basically my model is the following. Assume that we have a function p of x. This is exactly what I want to model. Probability of getting this y. So this is probability that y equals to 1 for a random item with given for example, if I write p of 47 in my example, I say that it is just a probability that random person, not from my data, but from some general population which I'm studying, that a random person from population of age 47 knows English. So this is some function that we don't know, but that we want to estimate from our data. We believe that this function exists. Actually, we can define it in this way. And we just say that we want to infer it from the data somehow. And how can I do it? Actually, my idea is to use something that is very close to my linear model. But as we discussed previously, we cannot put probability here because these values can be less than 0 or greater than 1. So I want to transform my probabilities to some other value that can take values from negative infinity to plus infinity. So all possible real values. And this is done in 2 steps. The first step is the following. So I convert probability. First step. From probabilities to chances, odds, they called. What is odds? This is the following thing. Probability divided by 1 minus probability. This is called odds, по-русски шансы. And this is actually a known a known thing. For example, if we say that probability to win is, okay, if I say that my chances to win is 1 to 1, what is the probability to win? So for example, if I say that odds of winning is 1, 1. What can I say about probability of winning? Yes, it is 1/2, because odds 1, 1 is like chances 1 that I win and 1 that I will not win. Шансы выиграть 1 к 1, по-русски так говорят. Если говорят шансы выиграть 1 к 1, ну, значит, с вероятностью 50% выиграю, с вероятностью 50% проиграю. So if I put this probability 1/2 to this formula, I will get 1. So a probability 1/2 is converted to value 1 by this formula. Let me draw the following thing. Probability changes from 1 to 0. What can I say about odds? What is the least possible value for odds? What is the lowest possible value for odds if we see at this formula? 0, yes. If probability is 0, then I divide 0 by 1 minus 0, and this is 0. And what is largest value for odds?
Infinity.
Infinity.
If peaks 1.
Yes. If this probability is close to 1, then it means that. So let me. If pair is close to 1, then we have something like 1 divided by 1 minus something very close to 1, like something like this. So this is something that is close to 1 divided by something very small. To divide by something very small, it is the same thing as to multiply by something very big. It means that these odds can be made arbitrarily large when probability tends to 1. Are there any questions here?
Am I right that if we have the 100% probability, these odds are not applicable, but maybe on the other hand, it's a very rare, if possible, situation when it is 100% probability?
Yes, yes, you are correct. Yes, odds are not odds are not defined for probability 1 because we have division by 0 in this formula, or we can say that odds are infinitely large for probability 1, but at least in the model that we will discuss now, this situation just never happens, just because we do it in this way.
It's interesting that in Russian we cannot say shansi if we want to describe situation of 100% probability, we also cannot say shansi about this. Like,
Ну да, мы говорим шанс 100%. Да, можно сказать шанс 100%.
Даже так как-то уже не очень звучит, потому что шанс как будто предполагает, что, простите, что есть вероятность, что нет. Мне кажется.
Ну да, в общем, okay, mathematically odds are like this. So now you see that we shifted from this segment from 0 to 1 to this large array from 0 to infinity. So this is our first step. But this is not yet the solution, because we want, basically we want to write some model like something equals to linear function. And we want this something to be able to change from negative infinity to plus infinity. So we have to do the second step. And can anybody suggest any function that allows me to convert this array from 0 to infinity to the whole line? Some function that is defined for positive numbers and whose values are all numbers from negative infinity to plus infinity. Are there any function with these properties? Well known. Корень. Нет, корень принимает только положительные значения. Square root is always positive, so it doesn't allow us to do what I want to do. I want something that transfers me this thing to this thing. Other suggestions? Logarithm. Yeah, Elena is absolutely right. And we have logarithm. So our second step is to convert odds to log odds, or sometimes called logits. So we just apply logarithm to odds, and we have this function. So let me recall how logarithm works. Logarithm is a function that is inverse to exponential function. Probably today everybody knows how logarithm function looks like, thanks to COVID epidemic. This is some positive outcome that everybody knows that exponential function is like this, and logarithm is an inverse function. So it is symmetrical one, and it looks like this thing. Половинка плюс p разделить на половинку минус p. Further, in this case, you have discontinuity at point 1/2, if I understand your formula correctly. And this is not what we want. We want something monotonic. We want something that is continuous and monotonic. Otherwise, it will be not easy to interpret it.
Okay, thank you.
So logarithm is really very good choice, and very natural choice due to some reasons. And so we have this logarithm. So we see that if that when odds take values here, this logarithm of odds take values over all the line. So we can write the following formula. We can say that now our model is this. Something like this. So now it is correct to write it in this way, because this value can be a positive, negative, whenever you wish. By the way, if we have 0 here, what is the vertical coordinate of this point? What is exponent of 0?
1.
1, correct. And it means that this point, which is related to this point, has horizontal coordinate 0. So we see that for odds that are larger than 1, we have logarithm larger than 0. And for odds less than 1, we have logarithm less than 0. And for example, it means that what probability corresponds to this point? Where, for example, what is if log p x1 minus p of x equals to 0? What can you say about p of x? Which value of p of x corresponds to this value? So which probability corresponds to this point? We see that this logarithm equals to 0 if chances are 1. And which probability corresponds to chances 1? No, not 0. Chances 1, just like 1 to 1. What is the value of probability? Yes, it corresponds to probability 1/2. So in a sense, this thing is rather natural. If it is positive, then probability of getting 1 is larger than 1/2. If it is negative, then probability to get 1 is less than 1/2. So this is rather natural symmetric situation, symmetric function. So if log greater than 0, then it means that p of x greater than 1/2. So if these logit are greater than 0, then probability that we have 1 is larger than probability that we have 0. Yes, 50-50, correct. So.
Excuse me.
Yes.
And maybe it would be useful to see to look at the curve of the of this p probability of x divided by 1 minus probability of x.
I will draw a graph. I will draw a graph. So you want to draw this graph of this function?
Yes, to take a better idea of how works this.
Okay. So we have p, and we have here p over 1 minus p, and this function works in the following way. It is 0 here, and it goes to infinity. So it is something like this. Actually, it is a hyperbola, so we can continue it here, but it does not make sense. And we can also continue it. So if, for example, if p is close to, yes, this is, if you draw the full graph, it is a pair of hyperbolas like this and this. But what is important for us is that this function, if we consider this function only on this segment, then this function is from 0 to infinity. Okay. Good. So I want to draw another function. Actually, the next step is to find how we can figure out p of x as a function of x. Now it is given in an implicit form, and I want more explicit relation. So I can write down the formula now. If you are totally afraid of mathematical calculations, you can probably it will not be very bad if you skip it, but just let us try to understand how it works. So we have this thing, and we know that logarithm function is inverse to exponential function. So let me find an exponential of both parts of this equality. And this is exponential of logarithm of p of x 1 minus p of x. And it equals to e to the power this thing. Let me denote just to just not to repeat this formula again and again, let me denote it by one variable z. So I have the following formula now. E to the power of logarithm of p of x 1 minus p of x equals to e to the power of z. What can you say about this thing? This is exponential of logarithm. What is exponential of logarithm? Exponential of logarithm of something. For example, let me use how can we find logarithms? For example, what is logarithm of e to the power 2?
It's 2 logarithm of e.
This is 2. Yes, let us assume that we have logarithm. Let us assume that log is the same as ln, so it is natural logarithm. So we know that logarithm is just by definition, logarithm is such a number that we can take exponential of to take this number. So what can we say about e to the power logarithm of e to the power 2? If we have this equality, then this is e to the power 2. So you see that this is the same thing as this thing. Okay, if you believe in this equality, then this equality also holds, because I just do the same thing with both sides of this equality. And we see actually that instead of e to the power 2, I can put here anything. Okay. Now let me repeat the question about this thing. How can I simplify this thing?
But is it still true that if we have, for example, 0 in let's say,
Here?
if here we have 0 instead of 2, will it still work?
Yes, sure. Logarithm of e to the power 0 is logarithm of 1, and logarithm of 1 is
Right.
0.
And there is no I just wonder if there are some maybe problems with the the set of definition, like when we just say that this equals to like log from e square is 2. Yeah, okay, it's equal to it's equality, but do we have the same how to say?
Yes, we have the same. We have actually this relation works for all values here. This is like a definition of what inverse function is. E to the logarithm of something y equals to y. This works for all positive y. For negative y, logarithm is not defined, but for all positive y's, this formula works.
So if it is defined, it works the same way.
Yes, 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 yes.
Okay.
This is in a sense definition. This is in a sense definition of what logarithm is. Logarithm by definition is an inverse function to exponential. So if we apply exponential, if we apply logarithm then exponential, they just cancel each other, and we recover this value. You can say it like this. The only possible problem here is like logarithm of 0 and logarithm of negative values, but we don't consider them. So I can rewrite this thing actually as just this thing, and now I have the following. This is p of x over 1 minus p of x equals to e to the power z. Then I will do just some high school algebra. I just multiply everything by the denominator. Then I expand the right-hand part. Then I move this here with opposite sign. Then I will collect terms here. Then I divide everything by this thing. Then I can divide both parts of this fraction by e to the power z. So and 1 over e to the power z. This thing is also can be rewrite as e to the power minus z. So this is our function. I can recover what z is, and I can write it in the following way. Like this.
Sorry, maybe weird question, but why it is more simple to have just one e with negative sorry, степень.
Yes, yes. It is just easier to follow the properties of this function when we have argument only in one place.
Okay.
For example, I can ask you if beta 1 is positive, what can you say about this function? Is it increasing or decreasing? If beta1 is positive. Some properties.
Decreasing.
Let us look at it. For example, if beta1 is positive, then e to the power minus this thing. What can I say about this function? Is it increasing or decreasing?
Yeah, increasing.
This thing is,
So, okay.
this function is decreasing, right? Because exponential is increasing, but I have minus here, and if beta1 is positive, then everything here is decreasing and exponential function is decreasing, right? And if this thing is decreasing, this thing is in the denominator of some fraction with fixed numerator. Then if this thing is decreasing, then the value of this fraction is instead increasing. So I have this thing increasing. Okay. So we can think a little bit about other properties. For example, if x is very large, what can you say about p of x? Again, I assume that beta1 is positive. If x is very large, what can I say about p of x? For example, if I have something like 1 over 1 plus e to the power minus 5x. Let us consider this function. If x is very large, then it's also large. How large? So if x is very large, then what can I say about this value? E to the power minus 5x. Actually, e to the power minus 5x is like 1 over e to the power 5x. So if x is large, what can I say about this thing?
It's very small.
Small, yes, it is very close to 0. So this value is basically 0. And some very small number. So numerator is just a little bit larger than 1. And this fraction is very close to 1. So this is like 1 over 1 plus something rather small. So this is very close to 1. Okay. So if x is very small, I mean very negative, what can I say about this expression? Like this one. In this case, e to the power negative 5x is instead very large value. And this fraction very small value because I have 1 divided by something very, very, very large. So p of x is close to 0. Okay. So basically, our function looks like the following. Something like this. It will never approach value 1, but it can be very close to it. And the same way here. Does it look plausible for you? Does it make sense? Mm-hmm. Okay. Then let us discuss a little bit more these values, beta 0 and beta 1. Actually, we have a family of these functions. Like we have, like previously, we had a family of straight lines that the choice of a particular straight line depend on the value beta naught and beta 1. But now we have a family of these curves for which, again, the choice of this particular curve from this family is done by choosing of these two numbers. So this is a two-parametric family, and it looks like the following. So we have p of x equals to so if we change beta naught, it means that we just move this curve to the right or to the left. So this is beta naught. Beta naught shifts this curve to the right or to the left. And we have the second parameter, beta 1. How do you think what beta 1 should do? If I make beta 1 larger, for example, it is positive, and I make it larger, what happens with my curve? Растянется, я бы сказал наоборот. Если я делаю больше, то скорее сожмется, чем растянется. So look, the larger beta 1, the faster this thing growth. So it is natural to assume that this beta 1 defines how fast our function growth. So if beta 1 is large, then we have faster growth. And it means that if we have small beta 1, this is like beta 1 greater than 0 and small, and this is like beta 1 greater than 0 and large. So if I increase this beta 1, it becomes more steep, more sharp. Okay, does it look plausible for you? Are there any questions so far? So we had a long journey, but let us return to the beginning. We began from this kind of picture, and let me rewrite this picture with our new settings. So we have some data points. And we want to fit some curve from our family to these data points. So we want to fit something like, okay, I don't have, sorry. I want to fit this curve, the curve from my family, to these data points. In other words, I want to select my parameters beta 1 and beta 0 in such a way that this curve fits my data in some good way. But again, I have to define what does it mean to fit in a good way. So this is, for example, H, and this is English. Okay. Then we have another story. This is called maximum likelihood estimation. Okay, I see that it is not very convenient to write without stylus, but my stylus is out of a battery. I think let us do the following thing. Let us make a 10 minutes break right now. Then we will return to the lecture for 15 minutes more, and then we continue with the second part with R. Okay. So now 10 minutes break. Okay, we continue. Everybody ready? Okay, so now I will present actually a very generic way to estimate parameters of some model, which is called maximum likelihood. And it works in the following way. Assume that we have some data, like this data that is shown on this picture. And I want to choose the best fitting curve. Let me first consider some example and discuss our intuition. Let me consider 3 possible curves. This is one curve. Okay, let me add some data point to make things more obvious. Let me put some points here and here and here. And then let me consider, for example, this curve. This curve and this curve. I have 3 curves now. This is number 1. This is number 2. And this is number 3. Which curve would you prefer to use if you have the data that are shown on this picture?
The first one.
The first one. Are there any other options, other opinions? So everybody like the first one, the first curve. Why? Can you explain?
Because it's closest to our data points. It has the minimum residual squares, if we can apply this notion here.
Well, yes, in a sense, but actually, if we are speaking about probabilities, we have to be accurate, because to find just squares of differences is not so natural here. But for example, if we compare curve number 1 and curve number 2, on one hand, we see that this curve number 2 is very close to these points. But what's the problem with curve number 2? Why we do not like curve number 2?
It's far from other points.
Yes, it is not very good at predicting these values. Here, in this region, we see a lot of data point with value 0. But our curve predict that at these values of x, probability to get 1 should be rather large, because this curve is now, it is just a probability. And what about number 3? What is bad with number 3? Why we prefer number 1 to number 3?
Maybe it's too far from the points which are in the внизу.
Yes, again, we can say that it is far from this point. So in these points, our model predicts that we see, well, at these values of x, the values of probability are closer to 1 than close to than to 0. So we have here a probability less than 1/2. But anyway, in these points, okay, we predict that it is more likely to get 0 than 1 at these points, but we can be more convenient, because we see almost exclusively points with value of 0 here. So we can make these predictions more convinced. We can put this curve here. So basically, indeed, out of these 3 curves, curve number 1 is the best one. But let us try to formalize this intuition. Our intuition is the following. For each data point, we have xi and yi. Let us consider some particular data point. Let me put some numbers on the graph. And let us consider some data points. For example, let us consider this data point. Let me assume that this is x1. This is point x1, y1. And I fix values beta naught and beta 1. Then I ask the following question. What is the probability to get point? Okay, I have to put some numbers here, like 50. That we actually got. Provided that model is correct. So if the model is correct, then P of X equals to 1 over 1 plus e to the power this thing. How can you answer this question? Let me assume that I have beta naught and beta 1 in such a way that my curve is this green curve. So so I consider now only this green curve. I can actually erase another two curves. And my question is, what is the probability to get the point x1, y1, this point? Any suggestions?
2 divided by 3, isn't it?
2 divided by 3 and 1 divided by 3. There are two options. There are two suggestions. So are there any other suggestions? So no, they are 1 over 3 or 2 over 3 or okay, not so much numbers on the graph that we can start with. So yeah, it probably have to be either 1 over 3 or 2 over 3. So what is the final answer? Now that the question is, what is the probability to get my point that I already that I actually get? So the points that I actually get are drawn here in this graph with these points. So I pick a particular point and I ask, what is the probability to get this point? In other words, I want to ask if the model is correct and I get a random person with age 15, with age 50, what is the probability that for this person I will get this data that I have? Let us recall what this curve means. Let us recall what is P of X. P of X is probability of what?
No, the answer is not 2 divided by 3.
So,
But
what?
1 divided by 3, because this is the probability of that this person knows English, right?
Yes.
Thus,
Yes.
the result is negative, that he or she doesn't know English.
Exactly. Yes. Look, P of X is probability to get y equals to 1. So this is probability to get point here on this line. And for this particular data point, we have probability according to model. We have probability to get 1 that equals to 2/3. But the actual point that we have lies not here, but here, as we see from the graph. So the probability to get this point is not 2/3, but 1 minus 2/3, so 1/3. So this is equal to answer this question. And the answer is, this is 1 minus p of 50. And this is 1 minus 2/3, and this is 1/3. Do you agree with me? So everybody who suggested 2/3, are you convinced that the correct answer is 1/3? Do you understand why? Okay, good. What about point? What about this point? What can I say about likelihood of this point? So this is likelihood 1/3. What about likelihood of this point?
But this dotted line actually goes on the curve, yes?
Yes, it should go. Yes, yes. This is a mistake in my graph. You're right. This dotted line should be like this. Yes. Yes. This is actually this number, and here likelihood is, after my fix, it is just 0.9. So if I see a point here, I just use the appropriate value from this graph. And if I see point here with value of y that is 0, I use 1 minus the corresponding value on the graph. And this thing is called likelihood. And this is likelihood of a particular point. And likelihood of the whole data set is just a product of likelihoods of particular points, because we believe that our data points are just independent on each other. And so probability to select 2 points from this model is just a product of probabilities. So probability of data set is product of all probabilities of all points. Not probability, but likelihood. It is better to say likelihood. Then I can say that if I have some data, and if I fixed this curve, I can find probability, I can find likelihood of this data. So if I fix this beta 1 and beta 2, I can find likelihood. Then my idea is very simple. I just will try to find the values of beta 1 and beta 2 that will increase likelihood as much as possible. So I try to maximize likelihood. And that's all. This is called maximum likelihood estimation. So let me check that the idea is clear with the following important example. Let me assume that my data looks like this. What can you say about the value of beta 1?
Maybe it should be relatively high because the 0 data points don't overlap
Mm-hmm.
positive data points.
Mm-hmm. Yes, let us consider three curves. Which curve corresponds to larger beta 1? So beta 1. Number 2, yes. This is largest beta 1. And smallest beta 1. This is number 3. What can you say about likelihood? Where likelihood is the largest? So which model gives us more likelihood? For example, if we compare number 2 and number 3, we see that these points give us large likelihood for number 2 because we have these values are closer to 1. And on the other hand, these values also give us large likelihood because here our curve is close to these points. So we see that the closer this curve to the corresponding points, the larger likelihood. So we have largest likelihood for number 2 and smallest likelihood for number 1. So we see that in this data, we want to maximize beta 1 as large as possible. Actually, in the limit, we will get something like this. We will get some curve that is very, 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 very close here, then very, 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 very steep here, and then very, very, very close here. This is like beta 1, very, very large. So this is a perfect fit case when we try to make beta 1 actually infinity. But this happens not so often in real data. And if it happens, we can just say, okay, we see that to the left from some value we have these values, and to the right we have another values. But anyway, it is useful to know that if we have this perfect separation of two classes, then logistic regression, just a regular logistic regression, will give us something strange. It can say you that it cannot converge. It can give you some very, very large values, and sometimes it gives you some warnings. This is due to this effect, that to make this curve very close to the data point, we have to make it infinitely steep, just like straight step here. That corresponds to negative. That corresponds to almost infinite beta 1. Are there any questions about this example? Okay, are there any questions about the whole lecture? Let me reiterate a little bit. So we discussed how to deal with binary categorical dependent variable. We said that we can encode it with zeros and ones. And then instead of fitting straight line, we fit this curve, which is called logistic curve, like this one. And then we fit it using this maximum likelihood idea in such a way that it goes close to our data points. And then we can use predictions of this model. We can interpret these predictions as probabilities. It doesn't mean that we recovered true probabilities, because we have a very strong assumptions about this function p of x. We say that p of x is in this form. In fact, it can be true, but most probably it is not true, because this is just some mathematical expression, but we really don't have any ideas why this formula should be correct in reality. But anyway, this is just like with straight lines in linear regressions. This is something that is convenient from a mathematical point of view, and that we can analyze easily and interpret easily. So we just use it as probably incorrect but useful model. Okay, so any questions?
Can I?
Okay, let me discuss a little bit more this likelihood thing. If we fix our parameters, we fix this curve. Then if we have data and this curve fixed, for each point in our data set, we can find likelihood of this particular point. We actually did it with this point and this point, and we can proceed with the rest of points in the same manner. Is it clear how we created how we figured out these likelihoods?
Yeah, when we have the curve, yes.
Okay, then for this curve, for all data points, we can find likelihoods and then multiply them all. Then we have just one number. So we have curve, we have number. Then we do optimization. We do optimization thing. We say, okay, we will find the curve with some algorithm that I will not going to discuss in details now. We will use some mathematical algorithm that allows us to find a curve that produces the best likelihood. And this is how we do it. Sarah, did I answer your question?
I think I just need time to.
Okay. Okay. So this is basically a thing that is very close to what we did with linear regressions. With linear regressions, we said that we have a straight line, we
Yeah,
have
we
a
did
sum
that.
of,
Yes.
yes,
But here,
yes. Here, just here, instead of minimizing these distances, we maximize likelihood. But basically, it is something close because the closer, in a sense, the closer this distance, the larger likelihood.
yes.
For example, here we have large likelihood because we have large prediction and large prediction of probability, and we have actual value 1.
I'm just
But,
thinking how to count that. But okay. Right.
Count what?
For instance, I have in my data a lot of points at, for instance, I have 10 people of the age 50 who speak English and 25 people who don't speak English. So I have kind of lots of dots here and lots of dots here.
Okay,
But
fine. Then you just okay, you have points here and points here. Then you just pick this point, count likelihood for this point. You pick another this point, count likelihood for another this point in the same way, and then multiply everything.
yeah. Okay. Thank you.
So, other questions?
And how do we go from the linear formula through this probability divided? Yes, a bit higher. How did we come to the logarithm? This formula, yes, which is our model. How did we gain it?
Well, in a sense, we just did it in a sense arbitrarily. I mean that we said that if P is probability, then this function of probability can take any values from negative infinity to plus infinity. Then let us model this value by some linear function. Why we chose this this function here? It is just some convenient way to do it. I don't have very good answer to this question. Why we had a linear function here? Just because linear functions are nice and we understand their property. Basically, this model is in a sense arbitrary, but it is important that this model catches some important properties of our dependency. For example, we can interpret this beta 1 as like we interpret it in linear models. We can say that this beta 1 shows how fast this thing that is something like probability increases as x increases, for example. So this is why this functional form is good. But I don't want to say that this formula is in any sense universal. This is just like linear function, something that is simple and that can be interpreted in the way that we want it to be.
Okay, thank you.
So, other questions? Okay, actually, it was possible to more or less ignore this part about maximum likelihood and just say that there is some magic that works. But I like to explain it in details because this method, maximum likelihood method, is very universal. if you have some probabilistic model and you have some data, you can try to fit your model to the data using this maximum likelihood. And it is very popular. If you ever will use some quantitative methods and beyond of just simple tests and regressions, you will most probably you will use this maximum likelihood paradigm. So it is useful to understand it. So other questions?
And what if we have beta 1 negative?
Mm-hmm.
The
Yes.
curve is reversed?
Yes, exactly. Exactly. If we have beta 1 negative, it means that this is decreasing dependency. So like something like this. Sorry, let me draw just a curve, not data. Something like this. So we can interpret, actually, we can interpret this beta 1, at least we can interpret sign of this beta 1 in terms that increasing of these parameters increase probability, for example, to know English. So if we get a positive result here, we can say, okay, we see that when people become older, the probability that they know English is higher. This is good to be able to give such interpretation. Okay. So other questions? Okay, now let us try to go to our studio and do some practice. I need to share my screen again. Some parts of another project. So let me create new R Markdown. I will use the same data set that we already used, that is related to adjectives and number of consonants. So do you remember this data set? And previously we used it to predict number of consonants from adjectives. But now I will do it in the opposite direction. It means that I will try to find how the fact that there are adjectives depend on number of consonants. And to do so, I have to introduce a new function that is called GLM, generalized linear model. And okay, let me show on some arbitrary example. Let me show how it works. Let me assume that I have some fake data frame. Let me assume that y is some variable that takes values good or bad. And I have something like this. Six. Okay. And let me use a linear model. I want to predict y using x. My data are fake data. And I have to provide something like family binomial. I think it should work like this, but I'm not sure. Okay. And let us look at summary of it. No, this is not what I want to do. Okay. You see a familiar output with estimates for coefficients. So they are estimates for our beta naught and beta 1. And let me draw some graph here. So we have these points. I use good as 1 and bad as 0. This thing actually calculates me a vector of values true and false, and true is the same as 1, and false is the same that 0. So I have this graph that corresponds to this data, and I can plot some curve here. Actually, I can use the curve that we discussed. So I need some numeric values. Okay, I think I can use curve here to draw 1/1 plus exponent minus let me try. Yeah. You see, these are our data points, and this is our curve. That corresponds to this maximum likelihood. This is just the result of this estimation. Okay, does it work for you? Let us try it just to see the effect that we discussed at the lecture. Let us try to make our data with perfect splitting. So I have to add, for example, good here. Okay, that's all. Let us try this data. You see that here I have a perfect separation. I have good, 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 good here, and bad, bad here. Let us try to do it. We see this warning, and we see some very large numbers here. Actually, it means that you don't have any reliable results that we can get here. And let us just try to make the corresponding plot. So you see that this curve is almost just here we have almost vertical line. So this is almost a step. And now, as a last exercise with this fake data, let us try to feed a different model. Let us try to feed a model without independent variables. For example, for the same data, let me assume that y does not depend on x at all. So we have only intercept here. How can you interpret this value? So in this model, it means that we have p of x equals to some constant. So for all points x, we have the same probability to get y. Y equals to 1. What can you say about this value? How can we interpret this value? Actually, was it possible to find this intercept without using R, just by some calculations? Or how can we interpret it? Any ideas? Okay, what is P of X? Just from the lectures. We have this data. In this data, we encode good as 1 and bad as 0. And what is P of X?
Probability to get good.
Yes. So for this model, we have that P of X just does not depend on X. It is some constant. How can we relate this probability with this number? First of all, if you look at this, data, what is your best guess about the probability to get good? If you have only this data and nothing more, and you believe that y does not depend on x, so we can ignore x, what is your best guess about probability to get result good?
Two-thirds.
Yes, we can just calculate it as we have 4 elements good, 6 elements overall. So our best guess is just 4 over 6, so 2/3. So we can expect that P equals to 2/3. Something like this. But here we have not 2/3, but something different, some different number. How this number is related to this number? So we can return to our model, and our model says something like this: that logarithm of P of X 1 minus P of X equals to something. This is the model that we discussed at the lecture, right? And now we have a little bit changed model. What is the difference between this model and the model that we used here? What is the difference? What is the difference of this general model and the model that we use now with this specification? I said that this model corresponds to this relation or this relation, how to reinterpret this relation in terms of this formula. If I want p of x to be constant, what should be changed here? If I want p of x to avoid dependency on x. Beta1 equals to 0, yes. So I can just remove this term at all. I get this formula. So let us check that this formula holds. So we can expect that p is this value. And what is beta naught in our results? Hmm?
Is it e power z?
If I rewrite this formula to find what is p as a function of beta naught, yes, I will get some value like e to the power beta naught. But I ask you about the relation between this model and the result of this regression. As you remember, we have these estimates. For example, when we fitted just a usual model when y depends on x, we have estimates for two coefficients, for intercept and for coefficient for x. So here are our estimates. And now we fit a simple model when we don't have dependency on x at all. So the output of this model is simpler, and I want you to relate this beta naught in this formula with something in this table.
I'm not sure. I don't feel confident with the term intercept, but isn't it the intercept?
Exactly, yes. Intercept is actually this free term that is usually denoted by beta naught. So this is correct for these formulas. Here we have coefficient with x, and we have intercept, which is a free term, which is this beta naught. This is just like in previous lessons about. Okay, look at this formula. Here, this is beta naught, and this is beta 1. And I used this intercept here in place of beta naught.
So intercept is just beta naught, like this free.
Exactly. Yes.
Yeah.
Intercept is just a free term. По-моему, по-русски, я не знаю перевода на русский язык слова intercept. По-моему, так и говорят, свободный член или что-то в этом роде. Okay. So we can expect that this formula will work if beta naught is this formula, is this number. Let us see that it is correct. I will just try to do it. Logarithm of, okay, let me put, and what is logarithm p over 1 minus p? Yeah, you see this, this is exactly this number. So in other words, this model, when I ask this model to predict me the value of probability that just do not depend on x at all, it gives us a correct prediction. Basically, we can do it in the opposite way. We can recover p out of this beta naught. So now I want it in the opposite direction. Here I get p that equals to 2/3, and I get this this beta naught. Let me do it in the opposite direction. Let us recover p out of beta naught. How to do it? How to find p if we know beta naught? So, any ideas how to do it? So we have this relation. And this relation allows me to find beta naught if I know p easily using these logarithms. But I want it into the opposite direction. How to do it? We can actually use the formula that we discussed at the lecture. I just want you to see that this formula is applicable here.
So it's actually the formula that you have given to us, but without this beta 1.
Exactly. Yes. Yes. But which formula?
1 divided by 1 plus exponent of minus beta naught.
Let us check. Okay, you see that we indeed recovered the value of P with good precision. This is 2/3. So here we just switch from probabilities to odds and vice versa. This P is probability, and this value is logarithm of odds, logits. This value. So we have this formula, and we have an opposite formula for which we have so P of x equals to 1/1 plus minus beta naught. This is the same thing. Exp of something is the same as e to the power something. This is more or less theoretical things, but I just want you to see with your eyes that everything that we discussed at the lecture indeed works. At least these formulas for logits and probabilities. That the result that you get from R are indeed results that are related to these logits. Okay. So now I want you to return to this data set and try to do the same thing. I want you to answer the following question. What is the probability that language does not have adjectives if we know nothing about number of consonants? Fit then fit logistic regressions with full model. So I want you to answer on these 4 questions. Please try to do it by yourself and let me know if have any questions about it? If something goes wrong?
In the second statement, there is check that it is in agreement.
Mm-hmm.
Yes. Okay.
So you have to answer question number 1 without regressions, just by analyzing the data set. And you can check that the result have to be in agreement with the fit of this logistic regression with model when p of x is just a constant. So it have to predict exactly the probability that you find on the first step. But we just have to make sure. Actually, I don't know how it chooses which variable to count as 1, which value, which level to encode as 1, and which level to encode as 0. I think that it is just a first element that is counted as 1, but probably I'm wrong. So you have to investigate it as well. So if you need any help, just let me know. I can look at your code and say something, or I can show you some other parts of my code if you need it.
Can I ask about that this parameter family that is equal to binomial of link?
Well,
What is
yes.
that?
Well, actually, this function GLM can do not only logistic regression, but some other different types of regressions. And actually, this is some string, some magic string that says that we need logistic regression. Actually, this binomial family means that we assume that our value y is like a result of coin tossing. In this case, we have it only 1 or 0, but it is possible to use these linear models when you have, for example, some numerical outcomes, numerical y, but that have to be interpreted as the result of like coin tossing. This is what this binomial means. And this LingLogit is just a function that we use. Actually, this function with logarithms. I think this function is called logit. So we just say how we so on the right hand side here we have something linear, and on the left hand side we have some transformation of probabilities. So this transformation is called link function, and here our link function is logit. I think that if we omit it, then it will work in the same way. This is just, I'm just have to be sure.
But why it should work the same way if this formula?
I just believe that this can be default value for this parameter, but I'm not sure.
Okay.
Probably we can just look at the documentation and check this default value. Probably not. Probably here family is Gaussian by default, so it will not work here. Anyway, this specification is correct. Family binomial LingLogit. Okay, does it work? Okay, who succeeded with question number 1? Estimation for beta 1. Beta 1 is the coefficient that corresponds to our variable, our independent variable. So we get at it at estimate column, like here, x, and here this is estimate for the coefficient for x. So this is our beta 1.
Можно спросить по-русски один вопрос? Я не очень понимаю, вот как мы можем построить логистическую регрессию с моделью, что, ну, вероятность
Константа, да.
а,
Но
это
смотрите,
константа. Если, я думаю, что как бы логистическая регрессия это по определению вот с этой формулой с логарифмом, нет? Или-
ну, правильно, ну и что? Но смотрите, вот если у вас, если вы знаете, что логарифм вот этой штуки это константа, значит и сама эта штука константа. Ну, как бы у вас здесь правая часть, ничего не зависит от x.
Да, то есть эм, она не перестает быть логистической от этого, да?
Нет, не перестает. Ну, это просто такой, это в некотором смысле вырожденный случай логистической регрессии, но это логистическая регрессия. So the question was how it can happen that we have logistic regression for which p of x does not depend on x. And the answer is that this is like this thing. If we have only beta not here, so we don't have any terms with x here, then it means that this value does not depend on x. And this is only possible if p of x does not depend on x as well. So to say that we have a model with fixed probability, probability that does not depend on x, is the same as to say that we have only intercept. This is intercept only model. Actually, we can look at this formula, which is equivalent to this formula, and see that this says that p of x equals to constant, and this constant is this number. For fixed beta naught, this is just a constant. And we can do it in GLM just by specifying number one instead of variable here. We just say that on the right hand side we have only intercept. This intercept is denoted by just number one.
Y is like good, bad, yes, and X.
This was probably the first example, and this is the second example that we studied. So what is the answer for question number one? And how did you get it?
This is 0.37 and
Okay. And how did you get it?
I just get the length, so I just get the amount of languages with adjectives and divide it by the amount of all languages in the sample.
Okay. How did you find number of languages with adjectives?
I wrote like length of that, then chose.
Okay, I see. So actually, we can do this table function. Table dot and dot adjectives, and it gives me absolute values, and then I can, for example, divide by length of dot adjectives. So okay, if we answer this question, and then we have this value. But this was just my guess that logistic regression will use no as value 1. I'm not sure that the result is correct, but we will understand it when we will answer this question. What about this question number 2? Anybody succeeded with fitting logistic regression? Can you say me the who can say me the value of intercept? Mm-hmm. So Elena provided an answer. Anybody else have different answer or the same answer as Elena? Mm-hmm. Так. Okay. So anybody else?
So we can write nothing in the brackets of binomial. I just
So,
leave it empty, and but I didn't.
yes, I think it works. Yes, I think that LingLogit is the default option for binomial, but the whole thing. But binomial is not the default option for family.
Yes.
Mm-hmm. So I see three persons who did this number 2. Anybody else? Okay, I think I have to include these questions into your next homework, so you will have enough time to think about them. But now you still can ask me any questions. So anybody?
We are on which step? 3?
Currently on step number 2, yes, but if you are on step number 3, we can discuss it also.
Uh,
By the way, if the answer for question number 2 is negative, yes, we have to compare. Okay. Okay, so if we have intercept that equals to negative 0.53, what can we say? What is which level is encoded by 1? Yes or no? We can look at these values, and we can look here, and I want you to answer this question. If this answer is correct, I don't know, but people say so. So if we believe in this answer, then we can try to figure out which level is encoded by 1. Level yes or level no. We have just these two values. Sarah says yes. Why?
I just think that we have more no's, and as long as we have negative, that means that it is
Yes,
the
yes, exactly. If we have negative logit, it means that the corresponding probability is less than 1/2. And out of these two probabilities, probability of yes is less than 1/2. So it means that yes is the variable that is encoded by 1. The variable, the level of the category, the value of the category that is encoded by 1.
I didn't get why the what is less than 1/2?
Probability to get yes, according to our data.
Yes, but how did we get from the value of intercept? This is why not? Yes. So we
Yes.
should.
Look, we have function p of x, which is probability to get value 1. And we see that logarithm p of x 1 minus p of x, it equals to beta naught. And beta naught, as you say, here is negative.
Yes. Yes.
So if this thing is negative, then it means that this thing is less than 1. So if log of
Yes.
z is negative, then z is less than 1. And if p of x over 1 minus p of x is less than 1, then it means that p of x is less than 1/2. This is again that we discussed at the lecture when we said that if that the point 1/2 corresponds to, the point P of x equals to 1/2 corresponds to odds 1 to 1. So in this case, odds just 1. And this corresponds to value of logit that is equal to 0. So if it is negative, then we have probability less than 1/2. And then we have to conclude that it is the level yes that is encoded by 1.
But how is it done?
Именно.
Ну, почему получилось, что yes?
Почему Артак решил?
Да, это как случайно. Совпадение это, что как бы yes кодированный как один.
Я думаю, что совпадение. I don't know actually how it chooses which level to encode as 1 and which to encode as 0. We can probably look at the docs, but I'm not sure that it is written here. Okay, so we actually out of time now. So you have a last chance to ask me some question about this part. Okay, there is, I see. So according to the documentation, the first level denotes failure, so 0, and all other success. So the first value denotes 0, like here, no, and all other, like here, yes, is just 1. So I actually believed that there is quite opposite, but the documentation says something that is in agreement with the behavior that we see. Okay, so if there are no more questions.
А что это значит? The first level denotes failure.
Ну, тут такая терминология в этих самых, когда мы подкидываем монетку, как бы у нас, мы считаем, что нолики это какие-то, мы считаем, что мы делаем какой-то эксперимент случайный, и он может закончиться двумя условными результатами, либо неудача, либо успех. Значит, вот, ну, как правило, failure кодируется нулями, а успехи кодируются единицами.
Да.
Это просто такая общепринятая терминология в всей истории про биномиальные случайные величины.
То есть он все-таки сам посмотрел на эти no и yes и как
И он
бы...
взял первый, он первый взял нулем, то, что ему первое попалось, а то, что второе попалось, взял единицей.
Понятно. Можно было бы просто, ну, это было бы, может быть, удобнее, если бы он сам как бы, ну, смотрел на значение строк. Если они no и yes, то...
Нет, ну это ж нужно понимать тогда, что такое no и yes.
Ну да, но
это нужно отдельную эвристику писать. Ну вот, например, создатели языка разметки YAML написали, значит, эвристику, что там можно true и false кодировать как yes и no. В результате те люди, которые кодируют названия стран с помощью исошных кодов двухбуквенных, очень сильно удивляются, когда у них страны выглядят так. Там RU, Россия, значит, и там US, United States of America, да, Норвегия. Или наоборот, нет, Норвегия. Или там false, Норвегия. Так что тут с эвристиком надо осторожно. Okay, so I think that if there are no more questions, I think we can stop for now. Thank you.
Спасибо.
Bye.
Thank you.